Hi everyone, my name is Parag Pal and welcome back in the new numerical of steel structure. In this numerical, we are going to design a lap joint, okay, for a specific load. And this kind of numericals will definitely come in your examination for approximately 10 to 15 marks. So make sure you solve the numericals properly and you get the proper information, right? So to get this started, let me just explain you the numerical from start to end. Okay, so let's get started. First of all, let's understand the numerical. Design a lap joint to carry a service load of 350 kilonewton. So see, we have a load of 350 kilonewton. Okay, I should write somewhere. So let me just write P equals to 350 kilonewton. Perfect. The bolt are 20 diameter, 4.6 grade and placed in a double row. See, there is lots of information given in a very single sentence. So we have 20 diameter of the bolt, 4.6 is a grade and it is mentioned in a double row. Okay, it means whatever bolt we are going to draw, we are going to design, like this. Okay, so this is our still, okay, right, which we are going to join, and these red colors all are the bolts. Understand, right? So we are going to do this design. So this diagram is a design of lap joint. Understand? Now, so it is placed in double row because this double row sentence is very important, right? I need to just highlight this. Plates are made of two flats 10 thick. So now the plates which is made of the flats, they are having, okay, 10 thick. The thickness is provided for the plate now. And we need to follow the steel grade as a FE 410. Okay, so this is the basic data available with us. So the FU will become 410. So you can refer here. The FU become 410. Okay. FUB become 400 megapascal. Okay. Right. And also we have the load over here. Correct. Also we do have the bolt of M20 diameter. So our area A and B is 245 square. So this is what we calculate. I'll just show you one example how it is get calculated. Give me a moment. You can see in the last lecture, I have just explained you what is the formula for this. So 0.78 into AG, whereas AG is pi by 4 into diameter square, right? So 0.78. So for this numerical, your answer would be, you need to come here, okay? I'll just come in the numerical. So it will be this calculated by, give me a moment, it was 0.78, okay? So yeah, so it is 0.78 into AG, right? So 0.78 into pi by 4 into what is the diameter? We have a diameter of bolt as a 20 right? So 20 square. So you will get 245 Understood? Now we have a diameter of hole, okay? Of hole we are calculating. So whatever the diameter of bolt, 20, you need to add plus 2. So we got a hole diameter as a 22 okay? To insert the bolt properly. Now this is a given data, guys. We have calculated very simple. We have only calculated the area and diameter of hole. Now we need to calculate three to four steps to resolve the numerical. So first step is single shear capacity of bolt. We need to calculate the single shear capacity of the bolt. What is the single shear capacity? It is calculated by formula VDSB. This is a VDSB is used to calculate the single shear capacity of the bolt. And the formula is, you now, if you watch my video since start first lecture, you might understand what is the formula and how it gets solved. So FUV divided by 3 in bracket N into A and B plus NS into ASB divided by partial safety factor. So you have all the details with you. Okay. You need to put all the things over here. FUB is a 400 under root 3 as it is. N is single capacity. That's why we are considering 1. A and B we calculate as a 245. Now we don't have share, so we just put 0 and partial safety factor is a standard value of 1.25. So we get a VDSB value as a 45.26 kilonewton. Now in Newton it is 45,264 Newton. Understand? So VDSB has become 45.26 Newton. Now remember, VDSB and VDPB, these are the two values that we need to calculate. Whichever is the smallest, that value we need to consider for the design. Now let's understand that in the step 1, we have calculated VDSB. Let's consider this as a lowest value. Let's consider this. So we will jump to step number 2. So in the step number 2, we need to calculate first of all how many number of bolt we will be required, right, for this construction, for this design. So the formula is PU upon VDSB. So you can distribute PU as a P into gamma F. Now you might wondering why gamma F over there. Now we have a service load, guys. We don't have the factored load. See, whenever you have a factored load, it is mentioned here it is a service load. We don't have a factored load in the numerical. So whenever we require a factored load from the service load, you should multiply that with 1.5. Okay, so you can see PU become P into gamma F upon VDSB. Now we have a value of VDSB as a 45.26 Newton and P is our load which is available here. Okay, 350 kilonewton, right? And we need to multiply it by 1.5 to make it as a factored load. Understand? Now we got a number of bolt value as a 11.59, but we can't provide 11.59 as a number of bolt. So we should provide it as a 12 number of bolts. Perfect. So now we have provided 12 number of bolts over there. Okay. Let it be. Right. Now you can read this notes on my website, but it takes time to upload over there. So you can just refer my video from start to end. Now let's arrange this board in a double line. Why? Because in our numerical, we need to arrange in a double row. What does it mean? It means that these are the two plates, okay, and we are arranging in this particular manner. This is a line number 1 and this is a line number 2, right? So these two lines we need to make. So first of all, if we are arranging in a double line, we need to calculate the strength, right? We need to calculate the TDN, which is the strength of joint per pitch length, right? So that is calculated by how? Whatever is your strength, whatever is your single shear capacity, you need to multiply it by 2. Why 2? Because of this sentence of the double line. If it is a single line, you no need to multiply by 2. This is a very crucial part of your numerical. If you miss something here, you won't get any marks in the examination, right? Sorry, my mistake. Oh, sorry, my bad. Right. Okay. You won't get any marks in the numerical. So that's very crucial one, right? Okay. So now we are calculated TDN. So we get a value of 90.52 kilonewton. Correct? So this is a step number 2 complete. Now let's jump into the step number 3. So step number 3 is we are going to equate. It means whatever the strength of the joint we calculate over here, we need to make it equivalent with the formula of the strength of tensile capacity. To calculate what? The pitch. And what is a pitch? Pitch is nothing but, let's consider this is your one plate, gusset plate. Okay. And you are doing a bolt design and you are putting one hole here, one hole here, one hole here. So the center to center distance between this bolt is pitch distance and this is the edge distance. Understood? So this is a very crucial thing that you should understand in your steel structure design. Now, so this is a concept where TDN equals to 0.9 Fu upon gamma m1 pitch minus dn into thickness. You have all the value except the pitch. So you put everything and if you put in your calculator, you will get the pitch value as a 52.66. So round out is to the 60 mm, right? Once you make it a round off and make it a 60 mm, now we will also consider the edge distance lower than the pitch value, which is 40 mm. Okay, so now we have a edge and we have a pitch distance. Now let's jumping to the step number 4, and this might be the last step, okay, for the numerical. So step number 4 is we need to calculate VDPP. Okay, we are gonna calculate this VDPP. So first we calculate VDSB. Now let's calculate VDPP. But to calculate VDPP, we need to calculate this smart value, which is a kV, and K to